My name is Lester Roble, and I'm in Mr. Rankin's class to talk about my senior project.
Awesome.
Just a little background info, guys. I was in the 2-year program first for the robotics and RO, which is kind of where I got the background for this. If you have kind of like an undecisive atmosphere, you don't know what you want to do, it's definitely one of the best supplementary majors here. Even if you just go for that, it's an amazing program. You learn a great deal, and you get a great job just with the program. And it's like a 2+2 deal, so you can get that and then keep going for your 4-year and get out of here with 2 degrees in 4 years. So definitely something you want to consider. You learn a lot and it's a lot of fun. Great transition from what you're doing now. Basically for my project though, I'm doing a thermal assisted water evaporation using a vacuum. It sounds really complex, but basically it's just a drying oven for ceramics. What you do, a lot of processes nowadays are automated, so this is going to take a wet ceramic product, you put it in this oven, it brings it down to a pressure of a vacuum, like a rough vacuum, and removes any content of moisture from it. Inside, there's going to be heater elements, there's going to be gas flow inside of argon, and this is basically going to evaporate any water in there through vapor deposition, evaporation, and thermal energy. When you boil something up, it just steams out. What's going to make this project actually relevant to electronics, you can say, is that I'm going to be doing this whole thing with process control. Basically, you're going to take the entire system and you take what's called a PLC. If you guys ever seen any of those, go to a robotics lab, you'll see them everywhere. And they're used a lot nowadays. You program this thing, and then you allow the user to choose set points. I want it to go this hot, I want it to stay on for this long, and I want this much gas to flow in. And the user can pick all this from a nice screen called an HMI, Human Machine Interface. And after X amount of hours, days, time, weeks, it comes out, and hopefully your product is great. This is kind of like a block diagram. For those of you guys that don't know, block diagrams are very helpful for people to visually understand what you're doing. And you're going to be doing a lot of these for Mr. West's class. Over here, as you can see, we have basically the HMIs with the human interfaces with, touchscreen, push buttons, whatever, and then it goes to the PLC. The PLC reads those inputs and then takes decisions based on logic that's inside, and then controls those 3 variables: vacuum level, temperature, and gas flow, which all then directly impact what's going on inside the process chamber. So this is all kind of multiple subsystems, but they're all related into one giant thing. And it's very important that all these things work out together and performing ideally, otherwise you're going to have what's called intolerance to injection. And you'll see process control when you take those classes. It's very important that you have all your parameters in a very set pattern, because if you don't, small deviations will actually become big ones later on, because they're impacting other processes. So, basically how it works, it's set up like put something in. Then the user selects like a recipe, what they want to do with temperature, time, gas flow, ramp rate, that kind of stuff. And then the PLC basically takes all that data, the user hits start, go, whatever. And it does. And then after it's complete, the way I check if the water has been taken care of, you take a reading of it and you find out on like a mass scale, you can see the weight there, and then you can release that was obviously from the water that was in it and no longer is there. Things that this project uses basically a really good paper, what you learned in school that this project will apply to the test. So in this project, I have process control, one of the very big principles that we do in robotics here, and as well as control theory, we learn Newton, very good class. We learn a lot about how systems impact each other. I don't know if he's told you about the capstone semester, but it's something that you guys kind of got here late for. It used to be a 2-year degree, It's called nanofabrication. And they would send you to Penn State after your first 2 years here, and you would learn how they actually make the physical chips, like microprocessor chips, on substrates. And it's very interesting stuff. It deals a lot with vacuum. It's on the nano level, so it's extremely, extremely small. And you use a lot of the most modern instrumentation. You learn a great deal about many fields, like material science, biology, chemistry, and the stuff that you learn there really makes you understand how much we can do with our material.
Yeah, you were there 2 summers ago, right? Down at Penn State.
And basically they send you there for the summer. You know, you go there to Penn State, stay in the dorms, and go to their nanofabrication lab.
Yeah, a couple of these guys are interested. Hunter, aren't you interested in going? Who else is interested in going to nano? Yeah, Oliver? Yeah.
I would definitely consider it because of the fact that not only do you get experience with some of the most scientifically advanced tools that are available now, like I'm talking about like $1 million equipment. You know, you get electron microscopes, you get into clean rooms where there's absolute control of the environment. You know what I mean? Like a dead skin cell is going to cause something to stop working. It's that sensitive. They put you in suits, you learn safety protocols. You know what I mean? Like the chemistry involved is to the point where it's manageable for someone with our level of experience, but you can learn so much based on that. You know what I mean? So it's not something that's really intensive. You're going to have to apply yourself in terms of, I guess, book smarts, I could say is the best way to put it. Because over here we do a lot of hands-on, you know. At the end of the day, when you come to class, it's what you can show. You build a circuit, you evaluate it, you take measurements, that's your grade. Over there, you have to read a lot, regurgitate the knowledge, and then do it again for a period of 3 months.
Yeah, and then how many teachers would you say you have there? I mean, it's not just Terry Kuzma, 1 or 2, but look at all the engineers that manage the equipment, especially in the big clean room. I mean, it's amazing the skill set. Yeah.
There's, I would say, 3 teachers that are basically going to be your lecture instructors if you go for this, and the rest of them are TAs. And then when you go into labs, because it's always divided from theory and lab, and you can have a morning lab or an afternoon lab, and theory is always at 12. And when you go in there, they basically just when you go to lab, they sit you down, and there's different people from different departments working there. There's some people completing doctorate work for master sciences and material science. There's some people working on, you know, completing a research paper. There's people from the Navy that come in to do sensing work and you know, stuff that are kind of, you know, applied work. And all the stuff that goes on is, you know, that they're willing to talk about what they're doing, and it kind of further inspires you to do something else with it. It's really, it sounds kind of cheesy, but it's honestly a place where like you learn so much more about yourself and what you can do with your degree, because you're around all these people that have different, I guess, venues, but they're all in the same place doing something pertaining to the science. And it's a really great door opener, and it's during summer. So, you know, you go to Penn State, you meet people that are in the same boat as you are, and you have a good time. You know, don't get me wrong, but you walk away with some really awesome memories and some really awesome knowledge. And I can honestly say to this day that was the most fun I've had in college, especially coming from a place like this. You know what I mean? You guys walk down the street and see my girls, so you know, it's not really that great.
So anyway, sorry to distract you there, but back to your.
Yeah,
but this is related to nanofabrication because vacuum, of course, is a fundamental process for nano. You have to do many things in a vacuum. So.
Yeah. And like I said, control theory is one of the other aspects of this project. Control theory, obviously, you're controlling many different variables. Things like PID, proportional integral derivative. That's a type of sensing. It basically constitutes to how much response. So in this system, you know, you have things called deadband. So say you have a set point. A user picks a temperature of 100 degrees. And it starts off from room temperature. So a deadband is you're ramping up the temperature, it's going up, and you don't want to overshoot that temperature because it's going to waste energy, and it's going to make the process, it could be temperature sensitive. If you want a temperature to be right here, but the product can't handle anything more than this, if you overshoot it, you're gone. So it's very important to hit like a very good balance of the control theory aspect. That's where you learn about like Laplace transforms and transfer functions that kind of dictate how mathematically this all works out. And that's going to be a pretty big part of this, I think, based on just what I learned last year. And these are all classes that you learn, you know, later on. It sounds kind of scary, but honestly, if you just pay attention and if you know what you're doing, it's gonna kind of get there. Sensing and control, obviously, you know, I'm going to have thermocouples for temperature. There's going to be vacuum gauges for reading vacuum, and you know, the HMI, all that stuff, that's part of the control and sensing of it as well. And then data collection finally is going to be, on the HMI, you can see the real-time data, what temperature is inside, in what area of the chamber, process chamber, what vacuum is inside. So if you have a leak or something, or there's, you know, one of the heaters breaks, you can find out what's going on, so you're not wasting time running something that's not going to give you any valuable product. And this is just like a basic diagram of what's going on here. There's going to be gas flow. In this case, it's going to be argon, because the school, you know, doesn't really like anything dangerous. And basically, the gas comes in, and what the gas does is it basically allows for uniform heating. So when the gas is, argon is a very, it's called a noble gas. It's very stable. You know, it doesn't really react with anything. And when it comes in, it evenly distributes the heat, and also helps agitate some of the water out of the ceramic. So it's going to help speed up the process, and it's also going to be used for cooling at the very end, because it comes out of the tank. It's going to be colder than atmosphere reaches. So it's going to help cool down the chamber so we can get it open faster, and it's, you know, safe to handle. If you guys have any questions about the project or about where you're going to be going the next 4 years,
Yeah, so how big is it?
it's going to be about the size of this table. The chamber itself is going to be about half, but then you got all the wiring, all the electronics and stuff. There's going to be a PLC board in there, and I'm still debating if I'm going to use an actual PC, or maybe like a touchscreen interface for it.
So it's gonna be like you're building like your own oven, basically?
Yeah, actually, when I did the 2-year degree, this is what I did for it, but it was a very crude model. It was just, you pressed a couple buttons and it was on and off. You know, there was no automatic cycle, there was no real way to tell what the variables inside were as far as temperature, as far as vacuum level. Nothing was really there. It was just, it was a very crude on and off kind of deal. And it was great for robotics because, you know, you got a taste of everything, very small knowledge in it. But then when you take it to the level of what you learned before, you can see how much more you can advance the system just based on the stuff that you learned. And the thing about, I guess I could say, that pertains to this is in this major, you get a lot of problems. And you'll find this out, I guess, when you take all Macy's classes that are really heavy for analog systems and linear systems. It's kind of like Gosh's class, but you start using like extremely complex circuits. And they give you circuits and problems that are so difficult that when you get a real problem, it almost seems trivial. You know what I mean? And it's gonna frustrate you, but you understand that these people have been in this business for a long time, and they know what people want to see, and what you're gonna be asked, how you're gonna be asked to handle it. And you may think that they're, you know, busting your balls, that they're giving you a hard time, but honestly, what you learn from these people is going to be with you for the rest of your life. And it's going to, I've gotten offers from a lot of companies so far, just because of what I learned in the 2-year. And then being able to address the topics I learned in the 4-year just helped me that much more. So you guys are in a good position right now. This is where you're going to be. If you're sticking to this kind of stuff, you're going to be in a good position. And you have to understand that the guys that are calling the shots for you right now may seem like they're, you know, that they're hammering you with it, but it's because they know that if you know what they know when you leave here, you're going to be golden.
Good.
Anybody else?